Muted?
Yeah, it starts.
Okay.
Yeah.
Then let me introduce today's speaker. Christian Kehl is a researcher and lecturer at Utrecht University since January 2020. He received his undergraduate and master's degrees at the University of Applied Sciences in Wismar in Germany, and the latter of which with a combined thesis at TU Delft in 2012. Then he followed the doctoral trajectory at TU Delft and University of Bergen in Norway, and graduating summa cum laude with a PhD in mathematics and natural sciences from the University of Bergen in 2017. And then his academic career led to many European-wide research appointments, among other TU Delft and University of Amsterdam, and University of Bergen, A. Marcel in France, and Denmark Technical University, and the Fraunhofer Institute for Graphical Data Processing. And he is now with Utrecht University. He also has a postdoctoral researcher appointment at the Institute for Marine and Atmospheric Research on high-performance computing in Lagrangian ocean models, which we're going to hear about today. And the lecture appointment since June 2020 at our department teaching principles of computer architecture. His research interests cover challenges in high-performance computing and modern and exotic computing architectures, modeling and simulation of geophysical processes, and real-time parallel rendering and visualization of those simulation data. And recent advances in neural networks engage him to research the application of stochastic machine learning methods in forecasting of geophysical processes, and the impact that stochastic variability has on the forecast's uncertainties. So without further ado, Christian, the floor is yours.
Yeah, thanks. I'm on mute, so okay, very good. Yeah, and especially to hook up on this last point. So first of all, I welcome you all to the colloquium. I'm Christian, and especially the hookup to the very last lines is what I'm going to talk about today, which is uncertainty quantification in Lagrangian fluid models using machine learning stochastic methods. Now, that's a very long title and a very abstract one too, I see that. So what I'm going to talk about is first some kind of motivation, what motivated me to pick up this research, what is kind of like the application background. Then I will highlight some challenges with basically responding to real-world cases when using Lagrangian modeling methods. I will outline our approach that uses machine learning methods to do stochastic modeling. And this will lead to a rather abstract framework. I have at the moment a master student who is working on a, let's say, specific incarnation of that framework. And that's what I'm going to go into a little bit of detail in the method section. I can already show some first results about that project. And recently we extended this project into an AI Labs proposal that was granted. So I'm also going to talk how those two initiatives relate to one another. And then we'll just have a little bit of Q&A. So first of all, in terms of motivation, we all know that environmental issues are like forefront news nowadays, right? So it doesn't really matter if it's about climate change or plastic pollution of the oceans or sustainable energy. Those questions are like in the news each and every time. And the best idea to approach answering questions and like shaping the future world is to do research on certain issues in that domain. And Utrecht University has several ways of addressing questions of environmental issues. So first of all, we have the Institute for Marine and Atmospheric Research, where oceanographers and physicists model and study ocean currents to predict, for example, the influence of ocean currents on the climate, but also the transport of plastic pollutants within the ocean. On the other hand, Utrecht University also has certain research goals and research themes, and one of that is pathways to sustainability, where Utrecht University tries to foster research into methods that address a sustainable future. And within that direction, our department, ICS, recently opened AI labs, and one of those AI labs is AI and sustainability. And within that framework, there is funding and initiative to research themes or research methods, how we can use AI to provide for a sustainable future. So this is kind of like the legal motivation or the research motivation. And further in this talk, because we can't talk about climate change and plastic pollution and so on and so forth, we're going to focus on plastic pollution of the oceans and how we can address that with the help of machine learning and artificial intelligence. So, and if we talk about that, we need to talk about the status quo, which is coming from physics. So the way physicists do this modeling, or the way physicists model the transport of plastic pollutants in the oceans, is that they use computational fluid dynamics. And this can be done in two ways, either in a Eulerian or a Lagrangian perspective. So as a little recap, a Eulerian perspective is that we have like a gridded domain of the fluid, and we can calculate the fluid flow of the fluid flow of the fluid, basically, with things like energy conservation, mass conservation, momentum conservation. Within that modeling, we can also see that, okay, given that a certain parcel in our gridded domain has a certain quantity of plastic pollutants, how is this plastic pollutant dispersed within our gridded domain, right? By solving this equation in a finite difference scheme. This is one way to approach the problem. Another way to see basically the challenge is to say, okay, we model our plastic pollutants as particles. And we use a particle system to model the trajectories of individual plastic particles. That means that we have an underlying Eulerian flow field, and we advect the particles in time within this domain to obtain the trajectory of those particles. Now this plot basically only shows like one particle being advected with different integration methods, but you can advect like millions of particles at the same time, and then you get a holistic perspective of particles and how they are transported within fluid. In both cases, what we need in order to do this modeling is that we have a certain number of particles, either specifically as particles or as accumulation of particles within our grid cell. And those are time dependent, but we need at least their initial position. We need the flow velocity fields, which is a field quantity of velocity in u and v direction that are time dependent. And in addition, we have certain properties that are either of gridded nature or attributes of the particles. Think of it here like the shape and mass of a certain particle, which then governs basically how it is transported with the fluid. The output that we want to have is the particle density at the end of our simulation to see where all those particles end up with. So here we represent the flow velocities in this 2D stack of field data. In addition, we have our particles, which can be thought of as a tabular entity with certain attributes attached to it. And if we plot those attributes of the particles according to the position of the particle, then we can also derive ourselves these field quantities. Those information are then fed into the computational fluid dynamic modeling framework, be it Eulerian or Lagrangian, and we will come out with this map of particle density where high values, so basically very high intensities, show a high density of plastic, while areas with low density or with low intensity show a low density of plastic particles. And this is how we can basically tell then to people, okay, this is where plastic is going to end up. Are there any questions to it? So you can, by the way, you can ask questions anytime you want. And I see the raising hands, and then we have a moderator who could facilitate that.
Yes, I can.
Good. So this is a very nice framework. The problem is that some of those attributes are affected by uncertainty. So first of all, the flow velocities that we have, they are represented in this gridded nature, and they are limited by the resolution of the grid. This is not only a problem, or not really an issue when it comes to integration, because yeah, okay, like smaller parcels, wider integration, but the resolution of those flow models also mean that there are certain physical phenomena like eddies that are just not resolved within the flow fields, which means that we cannot really model that, and they have a big impact on the distribution of particles. There's also things that some of the physical attributes, for example, the dwelling speed in which like a particle goes from the top of the surface to the bottom of the ocean, this can only be coarsely estimated. It can't really be measured. It could be measured in a lab for a specific particle with a specific mass and shape. But then if we do this, if we calculate this in the lab, then we come to the next point of uncertainty, because if we measure those on a small scale, then we actually need to upsample those measurements. And yeah, if we have like a cube of 1 by 1 meter, upscaling this to the whole ocean comes with a large amount of uncertainty. Also, we need to make certain assumptions that what we are measuring in the lab is an average sample of the ocean, meaning it neither underestimates nor overestimates the values. And when we do the upsampling, we also need to do certain linearity assumptions that we can actually upsample what we have measured. So all this contributes to data uncertainty within our models. And the way that physicists address this is in two ways. First of all, you can explicitly model stochastic variability. So for example, we can model Brownian motions by jinking the trajectory of particles in a like pseudo-random fashion. This, for example, would kind of like approximate the results that we would get if we have eddies being resolved. But we can't really, so the stochastic or explicit stochastic way has limits, because, well, we can only estimate the uncertainty of the processes that we can actually explicitly model. There are a whole lot of uncertainties that we cannot model. And another way to approach this then is to say, okay, we are not generating just one model, one simulation run, but we run the simulation multiple times with a varied set of parameters, meaning that we have not only one value, for example, for the mass of a particle, but a probability density function that gives us a certain range of how the mass is distributed for certain particles. And this will lead us to a simulation ensemble. And this is how physicists usually approach this problem of uncertainty. The challenge comes in when the whole modeling meets the real world. So policymakers and the public, they're not really interested or not really trained to understand what ensembles actually do. If in this case, for example, if a policymaker, like for example, Mr. Rutte, if he opens the newspaper in the morning and sees like, okay, there's a container ship in the middle of the Pacific that sunk down and that now distributed all of its cargo as plastic trash in the ocean, then for him the question is like, okay, where does all this plastic in the end up, right? From this accident. So the policymaker can ask the oceanographer, hey, where's all the plastic going? Then the oceanographer says like, yeah, sure, we can simulate this. The oceanographer performs a computational fluid dynamics simulation, and he can give you this density map. And that is what he or she communicates to the policymaker. Now the policymaker can say like, hey, yeah, look at it, like we don't really know what kind of goods were on this ship, like what's the size of the particles, are they bigger, are they smaller, they can have a different composition. So how do you know that this density map, this plastic density map, is actually true? And the oceanographer would then say, okay, then we simulate this in a parameterized ensemble. We generate multiple scenarios, and then we can the oceanographer or the physicist says like, yeah, okay, under this and this condition, we have a certain distribution of the particles in this area that is like this, and but if the condition is different, like that, so you can go over like 100 different scenarios and talk about this. If you talk with policymakers, they're like, okay, like all this ensemble stuff is really not what we're interested in. Could you just give us like a 10%, 50%, and 90% chance that plastic ends up at certain beaches? And if the oceanographers ask that question, then this is a question that cannot be answered with the ensembles, because there is no real way to analyze this and derive those metrics. So the result is that this traditional approach is not sufficient to answer those questions from policymakers. That is because there are certain shortcomings. So the range of parameters that we can replicate within our ensembles is arbitrary. So you need to actually decide like in which range you actually are going to simulate a certain parameter within the computational fluid dynamics model. It also means that some of those parameters cannot really easily be interpolated, and it also only covers like a small subspace of all the solutions that would actually be possible, because you cannot just like run a billion ensembles. Not possible. Another shortcoming is that this Lagrangian and computational fluid dynamics perspective is mechanistic, right? Because you can only simulate what you actually define within the equations as being a phenomena that you want to include. Now, the ocean is a chaotic system, and therefore simulating a chaotic system with a mechanistic framework means that you cannot describe uncertainties reasonably well. The advantage of those ensembles is that we have existing simulations, and those provide a plethora of data, right? So this an ensemble can have 1,000 simulation runs. And this is data that we can use in another way to give a better approximation. Also, the great advantage here is that all those simulations, they are equally probable. There is no bias for a specific expression of the parameter. So those are advantages that we can use, and we can ask ourselves the question, okay, why don't we just use a stochastic modeling framework instead of a mechanistic one, which can account for natural variability? And as computer scientists, we know stochastic modeling frameworks. We know, for example, Gaussian processes that can be regressive or classified, that can simulate stochastic processes. We also have multi-point statistics, which is a different approach to stochastic modeling. And in a way, neural networks also are able to do stochastic modeling because they give you, given a certain, so if we want to predict a certain state with a neural network, we give it an input set of data, we let it predict, and the prediction is not only coming as one value, but also it attached to a certain confidence value, meaning that the prediction is in line with 95% of all the solutions trained. So in our approach, what we do is that we say, okay, we have those field values, the flow map, certain attribute fields, and our particles, and we have a set of parameters. And if we feed those information into a traditional Lagrangian computational fluid dynamics model, then what we get out of it is this density map. All of those information are time dependent. In the next step, we can say, okay, this information is something that we can take over in a training database. And if we now modulate our parameters, if we change the underlying fluid flow model or change the distribution of particles, and we generate a new scenario in our ensemble that is going into the database, then we build up this database with multiple scenarios that is sorted according to the different parameters. In the next step, we can use the training database that we collected here and feed the flow, the fluid flow field, the particles, and the resulting density map into, first of all, a pre-processing step where we can say, okay, we cut out a certain region of interest, because most of the time we are not really interested for a specific case to predict the global distribution of plastic, but more regional studies, regional examples. And then we feed the particles and the fluid velocity as input into a stochastic modeling framework. And we give the output here as a target, which means basically we have a supervised learning context here, where we can train a machine learning model to replicate those results. Now we can move this here. The output of this training procedure is, first of all, that we replicate the density map, but we can also give ourselves out the particle density function, probability distribution function, PDF, of the density map, meaning that this gives us a certain value or a certain quantity of how accurate our trained model is in terms of replicating the predicted particle density with the trained ground truth particle density. So we have a confidence map and we have the particle density map. This is what we train. And if we now get a certain scenario, like in my initial example, Premier Rutte opening the newspaper and seeing, okay, there's a certain distribution of trash within the ocean, where does all the trash end up? Then we can feed this information, the location of the plastic particles and the flow map, into a pattern replication framework, where we also give in basically the trained model that we have from the pattern recognition stage, and we replicate the patterns and basically predict the particle distribution for our given scenario, and also the confidence of this prediction. And this is our modeling approach now. So the sketched approach, I give that to you, is rather a framework blueprint than a specific method. It leaves certain space for exploration and experimentation, because obviously there are multiple methods that we can use at these points to generate like a specific method. But it also leaves further experimentation of what is the impact of including certain training data in order to predict the outcome. It fulfills our expectation, which is that it is based on physical knowledge. That is what we have our Lagrangian database for. It is variable in terms of the physical parameters that we want to set, the regions that we are interested in predicting, and the boundary conditions that we set in terms of the model. It is minimal in the bias or prior assumptions, meaning that there is no bias within the database. All of the scenarios that are within the database are equally likely to occur and therefore have no bias, which is great for having a training data set that has independent, statistically independent items. And it predicts particle density as well as the attached uncertainty or confidence. Right, so in our new approach, the idea would be that the policymaker asks again the oceanographer, hey, what is the plastic distribution of the plastic that was released here? The oceanographer uses the stochastic simulation and then can give a specific information on the plastic distribution and the likelihood of this occurring. And if now the policymaker says like, okay, what's the 10%, 50%, 90% certainty scenario here, then the oceanographer can just apply a threshold to this confidence map, multiply this with the density, and give the policymaker direct information that was requested. Now, there are certain questions still attached. So where does all our data come from, right? We talk about machine learning, about learning from the data. So where is all the data coming from? At Utrecht University, we are well positioned here because we have the Institute for Marine and Atmospheric Research and the Parcels Group, and they are conducting those experiments all the time. So if we look back in the literature database for the last 10 years of their case studies, they have roughly 60 case study articles in the database, and each of those articles includes multiple scenarios that can contribute to the database. There are a few minimal requirements if we want to integrate a certain simulation, a past simulation into the database. We need obviously the time frame, how long this simulation has lasted, that was replicated there, the integration time step for which the trajectories were computed, the number of particles that were released, as well as certain information about the methods that were used to generate the data. We need the trajectories of the particles themselves. Luckily, they are stored in a very standardized format, so they're easy to access with, for example, neural networks. We have the physical parameters, shape, mass, and density of the particles that we need to include. So they need to be logged too, but that connects rather well with how the data is stored. We need the particle density map for each and every simulation timestamp. And we need the underlying Eulerian flow fields. This is probably the biggest hooker here, because obviously for them those flow fields have developed over the last years. So the question is really, do you still have those original data? Another question is, so given that we have now this framework, what are those specific methods that we can apply here for region of interest extraction, for pattern recognition, and for pattern replication? So for region of interest extraction, that is relatively straightforward. We can say that, okay, we're interested in a region, we give this region a center point, and we just include particles based on the closest distance, so either with the k nearest neighbor approach, with a radial nearest neighbor constraint, or computing the natural neighbors of that point. We can do intersection tests between points and circles, points and squares, but also tell the policymakers, okay, can you just like draw an area here on this map? And then we can do a point and polygon intersection test to filter out the particles. In the end, we can also do a temporal sampling. How this works, we're going to see later. In terms of pattern recognition, I mean, we have multiple options there. We can extract geostatistical values. We can use the database as a database of training images, pre-process them in order then to be used by the replication framework. We can also just extract features from the particles and from the flow fields themselves, and then do a feature-based training. And in the end, we can also use neural networks, which we can train based on the data to replicate the particle density from the flow model and the particles. If we come to the pattern replication, we can use Gaussian process modeling, meaning that we have a certain expectation value of a distribution of a certain quantity, for example, particle density. And then we evaluate the measured particle density at a point with the particle density at a reference at a reference value, and then generate ourselves variograms that are used by the Gaussian process. Multi-point statistics is another way of handling this. Here we completely neglect the particle nature of it and just say, okay, we want to predict particle densities. We have a gridded domain, and we have a certain prior distribution of particles, which is, for example, or plastics, which is, for example, the particles that were coming from the sunken ship. And we go into our database, we check if this partial pattern that is replicated here is found in the database of all our prior images. So all our D of P. We extract the patterns for which this partial pattern would be the same. So all the patterns where we have those two parcels being equal to the current situation, and then we set the value of the center cell with the average value that is replicated by the database. And by that we can recursively fill the domain. And neural networks, I think we all, or many of us know already, we can use the trained neural network, which is a collection of perceptrons that are arranged in certain convolutional and hidden layers within a network. that gives ourselves a prediction in the end. This neural network is then updated according to backpropagation rules, and in the end we can use the pre-trained network to predict the particles or the plastic distribution based on an input flow and certain input particles. Are there any questions up until now?
I don't think there are any, so you can.
Good. Then I continue. So at the moment I am supervising now a student, Yahmit Zarna, here in the informatics department, who is working on a specific approach to this general framework. He is investigating the leading research questions of how well do those neural networks, or do neural networks estimate particle densities in Lagrangian ocean models, and how do certain network design choices affect the estimation uncertainty. So here it's really about not only like building a neural network, but seeing how certain choices in the design of the network, such as prior sampling, but also such as batch or like how is it? Batch sequencing, how, for example, the interlinking of certain layers, how this affects the uncertainty prediction of the particle density that is to be replicated. The core design building blocks are here that we use a distance-based sampling, and we constrain this in time to the trajectory of the particles. The training is based on a convolutional long short-term memory with the database of Lagrangian ocean models, and the prediction is done with untrained samples, so samples that were neither part of the test nor of the training set. And we also look on the varying spatiotemporal conditions, meaning that what happens with the prediction if we predict the particle density in a longer time span or in a shorter time span. What is if we use simulation data for the training that are done in a shorter DT or in a larger DT? So, and those design decisions are basically summarized here. So the sampling, the normalization, which is always tricky for physical data, the type of temporal prediction, because we can say we have, for example, a number of scenarios that we feed the network in. So then we have those time instances, we have our neural network, and then the network can give us one specific prediction for example, d at time t plus n. Right, so for a specific instance in time later, which is ideal for the application. On the other hand, we also have approaches for end-to-end where we feed the network, for example, with 3 scenarios, 3 instances in time, and the network here predicts the next 3 time steps, which is simple in terms of the network approach or the network design, which is also more reliable, just because we have a limited frame of prediction. The only problem is that, for example, if we want to predict the particle distribution in 1 year, meaning, for example, 366 time steps ahead, we need to feed it with 366 time steps before. So that's obviously a drawback. But the impact of those design choices is what my student is currently researching and currently writing his thesis about. There he uses flow fields coming from the CMEMS simulation, which is a Eulerian simulation model from the US. We use those particle trajectories. So here, all those green lines, those are particles that are moving in time through this domain. For the prediction, those particles are then subject to this region of interest extraction. And because my student is coming from India, obviously his interest is in the Indian coastline. No problem with that. So when he does this region of interest extraction, what we end up with is this region, the particles in there. Now the particles, they're moving over time, right? They're dispersing in the fluid medium, meaning that if we would keep our constraint to this area, we would constantly have particles moving out of our prediction area. And that would not be particularly helpful for the training of the neural network. What is then done is that my student extends the area of sampling to the maximum extent of the particles in time for the simulation. So we have a larger area to cover because the particles disperse, and this area is then fed into the neural network. The neural network itself, as I said, is built upon convolutional LSTM blocks. We use LSTM because we need the recurrency in the neural network to actually predict multiple steps ahead in time. Therefore, we need to have a certain memory of prior predictions. And we use the convolutional part here because we're obviously predicting a spatial trend, which also means that we need to make sure that particles that are predicted are not moving, for example, in land areas where there obviously cannot be any fluid particle, right? So in order to constrain the predictions to certain spatial trends and boundary conditions, we use the convolutional design of the LSTM.
Christian, maybe
Yes.
it's good to slowly
wrap up.
and to wrap up.
Yes. Okay. So how this actually works is shown here. We have certain time steps in the path, so four path time steps. We want to predict the ground truth, which is predicted in this example, and at the same time we get a confidence map that in this case here shows a yellow pattern for all the areas where the prediction is absolutely certain, and then a certain graded area for the lessening confidence in the prediction. Now, with an outlook to our AI Labs proposal or project, we see that this is first deep learning, so AI prototype for predicting particle densities over time. There are still several research questions remaining in this original context: how to keep track of individual particles, what to do with very long time scales, because there obviously we cannot constrain anymore the spatial space there, because that would be then the global space. And how do we handle, for example, particles that are beached on areas, right? They would leave the domain. How can we react to that? Which means that we need to configure our model, and in order to do this configuration, we need a regional study. And there we put ourselves together with the Galapagos Conservation Trust, as well as researchers from EMAU and from the Physical Geography Department to develop a plastic removal strategy in the Galapagos archipelago. Our project is titled Explainable Deep Learning to Improve Plastic Removal Strategies on Galapagos Beaches. Now, you might see like, okay, so the explainable part is really not addressed with what you discussed up until now. That's right. Because the tangible drawback that we see now with neural networks is that the network is working really nicely. The problem is that it's not explainable to laymen or to practitioners. After all, the network itself is a Taylor expansion of those arrays here, and explaining this Taylor expansion is really hard to comprehend for people. If you say it's also related to the next point that this Taylor expansion, the result is expressed in those weighted layers. And you have a lot of people who come then, especially from the physics department, and say, okay, tell me which of those weights, which of those weighted layers is actually responsible for example, mapping beaching patterns, or which is responsible for managing dwelling patterns. You cannot really say it like this, right? This is not how the network replicates its data, and it's also not helped by saying, yeah, the method learns from the data, because we also don't know how humans learn. So if you just say, yeah, the network learns from the data, it doesn't really help them to understand how these physical processes are mapped. And in terms of computer science, our research objective here is to find an explainable neural network design that links established techniques, for example, random forests, but also Gaussian processes, to those neural networks to make this more explainable to practitioners, and to basically for them raise the confidence in what we are doing here with neural networks and with our research. Yeah, and with that I would like to end my presentation and give the word to you for questions and answers.
Thank you very much. Let's have a round of applause for our speaker. We have an audience question. Arno, please go ahead.
Okay, thank you very much. And thank you for a very interesting talk. But somehow I must have missed something. And that is your handling of uncertainty. I got the impression that the uncertainty map tells you how well the neural net predicts the ground truth. The ground truth is such a simulation model. Well, then you're not handling the uncertainty in the data, but only the uncertainty in how good your neural net is in predicting the outcome of the simulation. What am I missing?
Yeah, so in that case, there's the other problem that the database needs to be a representative sample of what we know about how ocean currents work, right?
Yes.
Okay, and that is where we have, that's why we build the database from all those previous simulations. Let me go back to that slide. Yeah, because we built this database for training from the published literature in oceanography that is basically out there for the last 10 years, right? This does not only include like different simulations from one and the same department, but also simulations from other departments, and they include different aspects of the physical process. So some of the methods, for example, include something like dwelling velocity, or or physical processes like biofouling, where biological material attaches to the plastic to make it sink and reappear again, right? So some of those simulations include those phenomena, some of them don't. Basically, everything that we know about how the ocean works is included in the database. So we can't go any better than what we already know. One aspect here, and that is really for future research, is that we also have drifters, so like actual small plastic antennas that go around in the ocean right now, where we can track their position, right? And there are certain neural network designs like FlowNet, where we could derive the flow velocity model from the actual position of our particles. And those would certainly replicate nature because, well, those are real measured positions from the satellite, from actual particles that are running around in our ocean.
So if I understand you correctly, what you're basically saying is, well, we have this database, and that is in itself a good representative sample of how how plastic disperses over the oceans.
Correct.
And then each neural net has its own uncertainty in how well it predicts, but this latter part will average out over all these different scenarios.
Yes, exactly, because the network is trained on all the scenarios.
Right. Okay, thanks very much.
Yep, you're welcome.
Thank you very much, Arno. Are there any further questions from the audience? One small question is that the simulation models that you're using all employ a two-dimensional grid, right?
Currently, at least the way we're doing the neural network right now, yes. The database itself, though, the database, we also have three-dimensional or four-dimensional, basically 3D temporal models that actually go into deeper ocean layers.
Because the ocean currents are also layered, right, in 3 dimensions. Like
yes, exactly. But that opens a whole can of worms, which is a good point for for further studies and further questions, because 2D models are divergent, right? You have in a 2D flow, you have sources and sinks of flow, while the 3D ocean is non-divergent.
Yeah.
Right. So this dichotomy would need to be addressed then.
Yeah, yeah, and also these models are useful when you have larger parts of plastics, but they're not going to be very helpful for microplastics, I assume. Or
well, the research done by EMO and by the PASES group is on microplastics, right? So there we don't really care about. Because we work on particle systems, so we can attach just like any kind of attribute to those particles. It's more a question of like, does the underlying flow model capture well the kind of physical phenomena that you would need to understand the small scale processes. But this is why we, for example, I would, as a computer scientist, would be uncomfortable opening this can of worms. That's why I go to the database of physicists who have actually done those simulations and have already made those design choices, right? And then say like, okay, those are the simulations we can use and we can trust.
yeah. Thank you very much. Any other questions? If not, let's have one final round of applause for our speaker. And let me remind you that next week the colloquium will be in Rupert Blau. So it's not going to be in Minart. It's not going to be fully virtual. It's going to be hybrid again. And we will be in Rupert Blau. Thank you very much. Bilgeça, we can stop the recording. Can I stop it?